That faint starlight you see tonight is a message from the distant past. Ancient starlight is a cosmic time capsule, a whisper of light that has traveled across space for billions of years to reach your eyes. It holds secrets of the universe's explosive birth, the formation of the first galaxies, and the very fabric of reality itself. By the end of this journey, you will understand how we decode this light to read the universe's oldest stories. We will uncover how a single photon can reveal the conditions that led to stars, planets, and eventually to us. What does it mean that we can look back in time simply by gazing upward? Each beam of starlight is a detailed cosmic report. It does not simply arrive, it communicates, telling us the story of its origin through the language of physics. The color of the light, its intensity, and even its specific shade reveal the composition of a star, its temperature, and how fast it is moving through the universe. This is possible because every element in the cosmos leaves its own unique mark on light. Think of it like a musical note. A tuning fork emits a pure, specific pitch. In the same way, a cloud of hydrogen gas in space will absorb a very specific color from the light passing through it, creating a dark line in its spectrum, a kind of elemental barcode. When astronomers capture the light from a galaxy billions of light years away, they pass it through an instrument called a spectrograph. This tool acts like a cosmic prism, splitting the light into a full rainbow. Etched across that rainbow are those dark absorption lines, the chemical fingerprints of everything that light encountered on its immense journey to us. The most profound clue written in this light is a phenomenon known as redshift. As the universe expands, it stretches the very fabric of space, and the light traveling through that stretched space gets stretched along with it. Its wavelength grows longer, shifting its color toward the red end of the spectrum. The greater the redshift, the farther the light has traveled, and the further back in time we are looking. This is how a single beam of ancient light becomes a time machine, allowing us to directly observe the elemental makeup of the infant universe. We are not just seeing a distant speck of light. We are reading a chemical analysis performed billions of years ago. Capturing this ancient light requires instruments of almost unimaginable sensitivity. In the silent vacuum of space, far above the shimmering distortions of our atmosphere, the Hubble and James Webb Space Telescopes act as our ultimate time machines. Their enormous mirrors, polished to near perfection, function like colossal light buckets, patiently gathering individual photons that have been traveling through the void for over 13 billion years. These are not mere pictures, they are collections of cosmic evidence, each particle of light a day, a point from the deep past. Because the expansion of the universe stretches light into longer, redder wavelengths, these telescopes are specially designed to see in infrared light, allowing them to perceive the true color of the most distant, ancient galaxies. But collecting the light is only the first step. The true magic happens back on Earth, where scientists use an instrument called a spectrograph to unravel the light's hidden story. Think of a spectrograph as the universe's ultimate translator. It takes the gathered starlight and stretches it out into a detailed rainbow, a spectrum that reveals everything. Etched across this band of color are fine, dark lines, the unique chemical fingerprints of the elements the light has passed through. The position of these lines tells us the composition of a star, while their subtle shift toward the red end of the spectrum reveals its velocity and distance. This is how a project like the Sloan Digital Sky Survey has painstakingly mapped the positions of millions of galaxies, using their redshift to construct a three-dimensional model of the cosmos. These are not just maps of space, they are maps of time, showing us the grand architecture of the universe as it was in its youth. With these technological marvels, we have learned to listen to the faintest whispers of the cosmos, setting our sights on the very first light to ever shine. But to see the very first starlight, we must look even deeper, to a time before stars or galaxies even existed. We must find a way to observe the universe's very first picture, taken when it was just a newborn. This picture exists and it fills the entire sky. It is the cosmic microwave background, a fossil glow from the Big Bang itself. This is the oldest light we can possibly see, a remnant radiation that has been traveling for almost the entire age of the universe, since it was a mere 380,000 years old. Before this moment, the universe was a hot, dense fog of particles and energy, so thick that light could not travel freely. It was trapped. Then, as the cosmos expanded and cooled, a profound transition occurred. Electrons and protons combined to form the first atoms, primarily hydrogen. Suddenly, the fog cleared. The universe became transparent, and that trapped light was finally set free, streaming out in every direction. That first brilliant flash of liberation has been cooling and stretching for over 13 billion years, and we can still detect it today as a faint, cold whisper of microwave radiation that perfectly blankets the cosmos. This cosmic background is not a uniform sheet of light, however. It is imprinted with a secret code. Sophisticated satellites like the Planck Observatory have mapped this glow in exquisite detail, revealing tiny variations in its temperature. These minute fluctuations, mere millionths of a degree, are the most important imperfections in the universe. They are the seeds of all cosmic structure. Slightly denser patches of that primordial gas, revealed by slightly cooler spots in the microwave background, held just a little more gravitational pull. Over billions of years, these subtle wrinkles in spacetime would draw in more and more matter, eventually collapsing into the vast cosmic web of galaxies, stars, and planets we see today. By reading this pattern, cosmologists can answer the most fundamental questions. They can test theories of the universe's explosive initial growth, a period called inflation, and determine with stunning precision the universe's age, its composition, and even its ultimate fate. The CMB is the foundational blueprint, the first chapter written in light. Every ancient star we study is a later sentence in a story that began with this primordial whisper. That first cosmic picture, the CMB, was taken, and then the universe went dark. For millions of years, an immense cosmic quiet settled in. The neutral hydrogen gas that filled the cosmos was like a pervasive, invisible fog, absorbing the higher energy ultraviolet light that would soon emerge. This was the universe's dark age. But this darkness was not empty, it was pregnant with potential. In the hearts of those subtle density fluctuations from the CMB, gravity was patiently at work, pulling together the first clumps of matter. Then a profound dawn arrived. Somewhere in the vast, featureless expanse, the very first star ignited. This was not a star like our Sun. These first stars, known as population 3 stars, are thought to have been colossal behemoths, hundreds of times more massive than our own, burning ferociously hot and brilliant blue, and living short, violent lives. Their birth marked the beginning of a new cosmic era, the epoch of reionization. The intense ultraviolet light pouring from these first stars and the earliest galaxies began to tear apart the neutral hydrogen atoms that filled the universe, splitting them back into free electrons and protons. This process, called reionization, was like a cosmic sunrise slowly burning away a global fog. The universe was being transformed from an opaque sea of neutral gas back into the transparent cosmos we know today. We know this happened because we can see its final effect etched into the light of the most distant cosmic beacons, quasars. As the light from a quasar travels billions of light years to reach us, it passes through vast clouds of intergalactic hydrogen. If that hydrogen is neutral, it leaves a distinct, deep forest of dark absorption lines in the quasar's spectrum. By studying quasars at different distances, and thus from different times, astronomers have observed that this forest of lines gradually disappears the closer we look to the present day. This tells us that the epoch of reionization was largely complete by the time the universe was around 1 billion years old. But how did it start? And what were those first starlight sources really like? This is where the James Webb Space Telescope acts as our ultimate time detective. By staring deeply into the void, it collects the incredibly faint, stretched light from galaxies at the very edge of observable time. Galaxies whose light was emitted during this reionization era. By analyzing their spectra and their numbers, Webb is helping us understand how these early, faint collections of stars could have generated enough radiation to clear the cosmic fog. It is a story of transformation, where the first starlight did not just illuminate the darkness. It fundamentally changed the nature of the cosmos itself, forging a transparent universe where light could finally travel freely across the ages. These first stellar titans were fundamentally different from anything that came after. Known as Population 3 stars, they were the universe's original pioneers, composed of a pure, primordial recipe of only hydrogen and helium. There were no heavier elements, no carbon, no oxygen, no iron. This elemental purity meant gravity could assemble them into true giants, with simulations suggesting they grew to be hundreds of times more massive than our Sun. They burned at ferocious temperatures, shining with a brilliant, searing blue light, and their lives were spectacularly short. A star like our Sun will shine for billions of years, but these behemoths lived fast and died young, exhausting their nuclear fuel in only a few million years. Their brief, violent existence was not in vain, however. It was inside these cosmic forges that the universe cooked its first heavy elements. Through nuclear fusion, they transformed primordial hydrogen and helium into new atoms, like carbon and oxygen. Then, in cataclysmic supernova explosions, they scattered these newly forged elements back into space, seeding the surrounding gas clouds with the raw materials for everything to come. This was the universe's first act of recycling. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all created in the heart of a long-dead star. But these first supernovae were more than just element factories. Their violent deaths also triggered the formation of the next generation of stars. The shockwaves from these explosions compressed nearby clouds of gas, causing them to collapse and ignite. This is how we know they existed, even though we have never directly seen one. We find their chemical signature imprinted in the oldest stars we can observe. These ancient second-generation stars, which formed from the ashes of the first, contain a minuscule but telltale amount of heavy elements. It is a faint chemical memory, a whisper of inheritance from their gigantic progenitors. The hunt for a pure, untouched population 3 star continues, a search for a cosmic firstborn whose light could tell us the unaltered story of the very beginning. Their legacy, however, is all around us, written in the chemistry of every rock, every world, and every living thing. Galaxies are the grand archives of the cosmos, their light a chronicle of construction spanning billions of years. Each one began not as a finished masterpiece, but as a tiny, dense knot in the fabric of the early universe. These subtle wrinkles, the very same ones imprinted in the cosmic microwave background, were the seeds of everything. Gravity acted as the master architect, patiently pulling these knots of dark matter and gas together over immense timescales. They grew through a relentless process of mergers and accretion, with smaller protogalaxies smashing together to build larger, more complex structures. We can actually watch this entire assembly process unfold simply by looking outward. Because light takes time to reach us, a galaxy 1 billion light-years away is seen as it was 1 billion years ago. By observing galaxies at various distances, we are effectively viewing a cosmic time-lapse, from the universe's youth to its mature present. The earliest galaxies captured by the Hubble Space Telescope in its famous deep-field images were often small, irregular, and chaotic, blazing with the fire of newly formed stars. They are the building blocks, the cosmic toddlers. Compare that to the majestic, well-ordered spirals and serene ellipticals we see in our cosmic neighborhood today, and you witness the result of billions of years of evolution. The starlight itself is the data stream from this epic construction project. When astronomers analyze a galaxy's spectrum, they are reading its life story. The intensity of its glow reveals its star formation rate, telling us whether it is a vibrant stellar nursery or a quiet, aging city. The specific absorption lines in its light act as a chemical census, measuring its metal content, which increases with each generation of stars. Even the subtle shifts and widths of these lines can reveal how the stars are moving, painting a picture of the galaxy's internal dynamics and mass. This is how we piece together the life cycle of a galaxy, from its chaotic birth in the early universe to its eventual quiet maturity. Every photon is a time-stamped entry in a cosmic logbook, waiting to be read. This idea is the ultimate key to cosmic timekeeping. The speed of light is the universe's ultimate speed limit, a constant that governs how quickly information can travel. Because of this finite speed, looking out into space is literally looking back in time. When you observe a star 100 light-years away, you are not seeing it as it is tonight, but as it was a century ago. Your view is a historical document. Now, amplify that effect across billions of light-years. The most distant galaxies we observe are not just far away in space. They are snapshots from an era when the universe was in its infancy. This is where redshift transforms from a curious effect into our most powerful chronometer. As the fabric of space itself expands, it stretches the light waves traveling through it, shifting them toward longer, redder wavelengths. The farther the light has traveled, the more space has stretched and the greater its redshift. This shift is not a random change, it is a precise measurement. Astronomers quantify it with a simple number denoted by the letter Z. A galaxy with a redshift of 0 is relatively nearby. A galaxy with a redshift of 6, however, tells us its light was emitted when the universe was only about 1 billion years old. We are seeing that galaxy as it appeared 12.8 billion years in the past. It is through this meticulous calibration of redshift that we have pinned down the universe's age to roughly 13.8 billion years. Every point of light in the deep field images from our great telescopes comes with its own Z value, its own timestamp. This allows us to construct a definitive timeline of cosmic evolution. We can now place the earliest galaxies, the epoch of reionization, and the formation of the first heavy elements in their correct chronological order. This timeline is the essential framework that gives context to everything else we discover. When we analyze the chemical fingerprint of a distant quasar, we are not just identifying elements, we are reading a dated entry from the universe's own diary, a specific chapter in the grand story of creation. This method of stellar archaeology allows us to read the universe's elemental history like a vast, cosmic family tree. Each star in our galaxy's halo is a living artifact, preserving the chemical conditions of its birth within its spectrum. The oldest of these stars are remarkably metal-poor, containing only trace amounts of elements heavier than hydrogen and helium. Their composition is a direct chemical snapshot of the universe's youth, a time when only a few generations of stars had lived and died. By meticulously cataloging the precise ratios of elements within them, astronomers uncover a clear pattern. In these ancient stars, elements like oxygen and magnesium are far more abundant relative to iron. This specific signature points directly to a particular type of cosmic event. These alpha elements are forged predominantly in the violent, rapid supernova explosions of very massive stars. The high ratio tells us that the early galactic environment was enriched primarily by these short-lived giants, which seeded the cosmos with their specific elemental fingerprint before more diverse sources emerged. This is the universe's chemical genealogy in action. Later generations of stars, including our own Sun, formed from gas that had been polluted by a wider variety of sources, including the slower, more patient supernova from smaller stars that produce a different mix, rich in iron. By reading these chemical hieroglyphs, we can trace the entire life cycle of matter, from the first pure hydrogen clouds to the complex elemental diversity that made our own world, and ourselves, possible. The detailed ledger of elemental abundances reveals which stellar factories were operating at different cosmic epochs, telling us not just what the universe is made of, but how it built itself over deep time. The final brilliant act of a massive star is a supernova, a cosmic explosion of unimaginable power. In a single cataclysmic event, a dying star can outshine its entire host galaxy, becoming a beacon visible across the universe. But these are more than just spectacular light shows. They are the universe's most crucial element factories. Deep within the extreme conditions of the explosion, a frantic nuclear alchemy takes place. Through processes with names like rapid neutron capture, elements far heavier than iron are forged in an instant. The gold in a wedding ring, the uranium that powers reactors, the iodine essential for life, all were created in the heart of a dying star and then violently blasted into the void. This newly enriched material, mixed with the surrounding hydrogen and helium, seeds vast clouds of interstellar gas and dust. This enriched medium becomes the raw material for the next generation of stars, planets, and ultimately, living organisms. We are quite literally made of stardust, the recycled remnants of ancient stellar explosions. The light from a supernova itself is a precise scientific instrument. Astronomers have learned that a specific type of supernova, known as a Type 1a, always explodes with nearly the same intrinsic brightness. This consistency makes them phenomenal cosmic yardsticks, or standard candles. By observing how dim one of these supernovae appears from Earth, scientists can calculate its exact distance with remarkable accuracy. It was through this method, by meticulously measuring the light from distant supernova, that researchers made one of the most shocking discoveries of the 20th century. They found that these stellar explosions were fainter, and thus farther away than expected. This could only mean one thing: the expansion of the universe is not slowing down, it is accelerating, driven by a mysterious force we now call dark energy. A star's death scream, observed through its ancient light, revealed one of the deepest secrets of cosmic fate. We can still see the aftermath of these events today. The Crab Nebula is the expanding remnant of a supernova recorded by astronomers in the year 1054. Even now, almost 1,000 years later, observations in X-ray and optical light show a chaotic cloud of gas and dust, still expanding at immense speed. At its heart spins a pulsar, the incredibly dense, rapidly rotating core of the original star, which continues to pump energy into the surrounding debris. This nebula is an ongoing chemical laboratory, where new elements are still being synthesized and scattered into space. The legacy of these cosmic forges is written not only in our own bodies, but in the very light that travels to us from across the ages. As this enriched starlight journeys for millions of years, it must pass through vast clouds of interstellar dust and gas, which subtly reshape its message before it finally reaches our telescopes. But that ancient starlight does not travel through a perfect vacuum on its long journey to us. It must pass through a vast, invisible sea known as the interstellar medium. This sprawling expanse of gas and dust, spread thinly between the stars, acts as a cosmic filter, subtly reshaping the light's message before it reaches our telescopes. Tiny dust grains, smaller than a wavelength of light, preferentially scatter the shorter, bluer wavelengths, much like our own atmosphere makes the sky appear blue. This scattering effect reddens the starlight, making distant stars appear cooler and redder than they truly are. Meanwhile, the gaseous component of the interstellar medium, primarily hydrogen, leaves its own mark. As starlight passes through these diffuse clouds, atoms within the gas absorb very specific colors, imprinting a forest of fine, dark absorption lines onto the spectrum. These lines are a direct chemical assay of the cloud itself, revealing not only its composition but also its density and temperature. By meticulously studying these effects, astronomers can perform a kind of cosmic forensics. They map the invisible architecture of our own galaxy and others, tracing the distribution of this raw material for future stars. This understanding is absolutely crucial for correcting our observations of the most distant cosmic objects. The light from a quasar 10 billion light-years away, for instance, must first pass through the interstellar medium of our own Milky Way. We have to create sophisticated models to subtract this local interference, to peel back the veil of our own galactic neighborhood and see the pristine signal from the deep cosmos. This constant filtering process underscores why modern astronomy relies on observing across the entire electromagnetic spectrum. What is obscured in visible light might shine clearly in the infrared, or reveal its secrets in radio waves. By looking at the universe in all its colors, we learn to see through the cosmic haze, ensuring that the ancient stories carried by starlight are read as clearly as possible. To truly see the cosmos, we must learn to observe in all its colors. Our eyes perceive only a tiny sliver of the full electromagnetic spectrum, a narrow band we call visible light. But the universe broadcasts its stories across a much wider range, from the long, gentle waves of radio to the short, violent bursts of gamma rays. Each type of light reveals a different chapter of a celestial object's life. A galaxy that appears serene and structured in optical light might be revealed in radio waves as a turbulent cauldron of cold gas, the raw material for new stars. The same galaxy, viewed through an X-ray telescope, could unveil a brilliant, superheated atmosphere of gas, held in the immense gravitational grip of a hidden supermassive black hole at its core. This is the power of multi-wavelength astronomy. It allows us to see the complete picture, to read the entire book of a cosmic object, not just a single page. Consider a vast, dark cloud of dust in space, impenetrable to our optical telescopes. When we point an infrared observatory like the James Webb Space Telescope at it, the cloud suddenly becomes transparent. The infrared light, with its longer wavelengths, slips past the tiny dust grains to illuminate the stellar nurseries hidden within, showing us the birth of new solar systems that would otherwise remain secret. Meanwhile, ultraviolet light acts as a spotlight for youth, highlighting the hottest, most massive, and shortest-lived stars in a galaxy. By synthesizing all these views, we can chronicle the entire life cycle of a galaxy, from its dusty birth to the energetic phenomena of its maturity. This integrated view is essential because the light we have been following, the ancient starlight itself, is subtly shaped and redirected by forces we cannot see directly. The very path of light is bent by gravity, a phenomenon known as gravitational lensing, which often reveals the presence of the cosmos's most mysterious component, dark matter. The invisible hand of dark matter sculpts the cosmos in ways we can only perceive indirectly. This mysterious substance does not interact with light at all, yet its immense gravitational presence warps the very fabric of space around it. Think of spacetime as a taut, flexible sheet. Placing a heavy weight on that sheet, like a cluster of galaxies rich with dark matter, creates a deep dimple. Now, when a beam of ancient starlight travels across this curved landscape, its path bends, following the contours of the dimple. This effect is gravitational lensing, and it acts as nature's own telescope. Instead of seeing a distant, faint galaxy as a single tiny speck, we sometimes see it transformed into multiple, stretched, and magnified images, often forming brilliant arcs and rings of light encircling the foreground cluster. The Hubble Space Telescope has provided breathtaking examples of this, where the light from galaxies billions of light-years behind a cluster is twisted into a celestial mirage, a cosmic carnival mirror that reveals the unseen. By meticulously analyzing the precise shape and brightness of these distorted images, astronomers can perform a kind of cosmic cartography. They can map the distribution of the invisible dark matter that must be present to cause such dramatic bending. This allows us to weigh entire clusters of galaxies and confirm that what we see in stars and gas is only a small fraction of the total mass. This understanding is crucial for interpreting the light from the most distant reaches of the universe. When we measure the redshift and apparent brightness of a supernova to study cosmic acceleration, we must first account for any lensing effects that may have amplified or altered its light on the long journey to us. Gravitational lensing transforms an obscuring veil of darkness into a powerful analytical tool, letting us use the warping of spacetime itself to illuminate the secrets of the universe's dominant yet invisible architecture. This mysterious force, dark energy, now dominates the cosmic landscape. It is the reason the universe is not just expanding, but its expansion is speeding up, a discovery that fundamentally reshaped our understanding of cosmic destiny. This acceleration directly warps our view of the deep past. As light from an ancient galaxy journeys toward us, the space it travels through is stretching faster and faster. This relentless expansion does more than just redshift the light. It also makes the galaxy appear fainter and more distant than it otherwise would. It is like watching a runner on a track that is itself lengthening as they race, making their effort seem even more immense. We measure this effect through two key cosmic probes. The first are Type 1, a supernova, those perfect standard candles whose unexpected dimness first revealed the acceleration. The second is a subtler cosmic ruler imprinted on the universe itself, known as baryon acoustic oscillations. In the very early universe, pressure waves like sound waves rippled through the hot plasma. These waves froze in place when the cosmos became transparent, leaving a faint, preferred scale for the separation of galaxies. By measuring this standard distance in vast galaxy surveys, like a carpenter using a cosmic tape measure, astronomers can track how the geometry of space has stretched over billions of years. The data from both methods converge on a staggering conclusion. Dark energy constitutes about 68% of the entire energy density of the cosmos. It is the dominant component of the universe, and its repulsive gravity is forcing galaxies to flee from one another at an ever-increasing rate. This relentless expansion stretches the very fabric of space-time, and the ancient starlight traveling through it bears the imprint of that struggle. The light we collect is not just a relic of the past, it is a messenger from a cosmos being pulled apart. By reading its faint, redshifted signal, we are not only uncovering the history of the universe, but also predicting its ultimate fate. Will this acceleration continue forever, leading to a cold, dark, and isolated cosmos? Or could the strength of dark energy change, leading to a different, more dramatic end? The answers are written in the dimming light of the most distant stars, a story of cosmic fate that sets the stage for understanding everything else, from the grandest galactic clusters to the smallest structures taking shape within them. This grand cosmic architecture reveals itself not as a random scattering, but as an intricate, webbed structure. The universe is filled with immense filaments of galaxies, sprawling walls, and vast, empty voids, a pattern known as the cosmic web. These are not just shapes in space. They are a direct trace of the underlying skeleton of dark matter, the invisible scaffold upon which all visible structure is built. Gravity has spent billions of years patiently sculpting this web, pulling matter into dense knots and long, connecting threads, while leaving behind unimaginably large regions of near emptiness. To see this structure, we must map the universe on the largest possible scales. Projects like the Dark Energy Spectroscopic Instrument are doing exactly that, aiming to chart the precise three-dimensional positions of tens of millions of galaxies. By measuring the redshift of each galaxy's starlight, it places them in cosmic space, building a pointillist masterpiece that reveals the Webb in stunning detail. Within these maps, we see a dynamic history. Galaxies preferentially align along the dense filaments, like pearls on a string, slowly flowing toward the massive clusters at the intersections. Meanwhile, the voids between these filaments grow ever larger and emptier as the universe expands, their boundaries becoming sharper over cosmic time. The profound beauty of this is how perfectly the observed Webb matches the subtle patterns predicted by the cosmic microwave background. The tiny wrinkles in the infant universe have grown, through gravity's relentless work, into the vast cosmic metropolises and empty deserts we see today. The light from each galaxy in this Webb is more than a position marker. It is a history book. Its spectrum tells us not only where the galaxy is, but how it is moving within the gravitational tides of the Webb, and what its stellar population reveals about its long journey of formation. This entire, interconnected system, from the largest void to the densest cluster, sets the stage for the most extreme and influential objects in the cosmos, the supermassive black holes that reside at the very heart of galaxies, whose powerful forces can dictate the fate of everything around them. At the heart of nearly every galaxy, including our own Milky Way, lies a gravitational monster, a supermassive black hole. Most of the time, these cosmic giants rest quietly in the dark. But when a steady stream of gas, dust, and stars spirals into their clutches, an incredible transformation occurs. The infalling material does not plunge in silently. It forms a swirling, superheated disk of plasma just outside the event horizon, a structure known as an accretion disk. Friction within this disk heats it to millions of degrees, causing it to blaze with light so intense it can outshine every single star in its host galaxy combined. This is an active galactic nucleus, a beacon of raw power whose light floods the cosmos across the entire electromagnetic spectrum, from X-rays to radio waves. Often, these active black holes unleash colossal jets of particles, shooting out from their poles at nearly the speed of light, and stretching for thousands of light years into intergalactic space. This torrent of energy is not just a spectacle, it is a fundamental regulatory force. These jets and the powerful winds they generate can blast through a galaxy, heating the cold gas needed to form new stars or even blowing it entirely out into the void. This process, known as feedback, effectively puts a limit on a galaxy's growth, preventing it from becoming too large. The brilliant light from an active galactic nucleus, therefore, is not just a sign of destruction. It is a creative and limiting force that sculpts the galaxy it inhabits. To understand this dynamic, astronomers turn to the most luminous of these objects, known as quasars. The spectrum of a quasar is a treasure trove of information. Its broad emission lines reveal the frantic motions of gas in the accretion disk, allowing us to measure the black hole's immense mass. But its light also serves as a brilliant background lamp. As this light travels across billions of light years to reach us, it passes through countless clouds of diffuse gas in the intergalactic medium. Each cloud leaves its own unique set of dark absorption lines on the quasar's spectrum, a phenomenon called the Lyman alpha forest. By decoding this forest, scientists can take a census of the universe's invisible gaseous structure at the dawn of time. This intricate dance between the black hole's violent light and the surrounding galaxy is a central theme of cosmic evolution. The energy output from these central engines can either trigger bursts of new star formation by compressing gas clouds or quench it entirely by stripping a galaxy of its raw material. This delicate balance, written in the language of ancient light, ultimately sets the stage for quieter, more stable galactic environments where solar systems, and the potential for planets like our own, can slowly and peacefully take shape. This same ancient light also guides us to the cradles of new worlds. Planets are born in swirling disks of gas and dust that orbit infant stars, and the starlight illuminating these nurseries holds the first clues to their formation. As this light interacts with the disk, it is scattered and absorbed, revealing the disk's structure in exquisite detail. When astronomers point their most powerful telescopes at a young star, they often see its light sculpted into a brilliant, flat disk. Etched across that disk are dark gaps and bright rings, like the grooves on a cosmic record. These are not random features. They are the gravitational signatures of newborn planets. A young, growing planet clearing its orbit will sweep up material, carving out a distinct gap in the disk. The precise shape and depth of that gap, read from the pattern of starlight, can even tell us the approximate mass of the unseen world, a planet so young it is still shrouded in the dust of its own creation. We can also find fully formed worlds by watching for the subtle winks in a star's light. This is the transit method, a powerful technique that has revolutionized our search for other worlds. When a distant planet passes directly in front of its host star from our vantage point, it blocks a tiny fraction of the star's light, causing a minute but measurable dip in its brightness. Imagine a gnat flying across a searchlight miles away. That is the scale of the detection. Missions like Kepler and TESS are designed to monitor hundreds of thousands of stars simultaneously, their sensitive instruments patiently recording these fleeting shadows. A single, repeating dip reveals the planet's orbital period, its year. The depth of the dip tells us the planet's size relative to its star. But the true magic happens when we combine transit data with spectroscopy. As the planet transits, a tiny amount of starlight filters through the planet's atmosphere if it has one. The atoms and molecules in that alien air absorb very specific colors, leaving their unique fingerprints on the transmitted light. By decoding this faint signal, we can read the atmospheric composition of a world hundreds of light years away, searching for the chemical whispers of water vapor, methane, or even oxygen. This ability to conduct a chemical analysis from across the galaxy brings us to a profound question. The same elements that are essential for life on Earth are forged in stars and scattered throughout the cosmos. When we analyze the spectrum of a star, we are taking a census of the elemental building blocks available in that system. A strong presence of carbon, nitrogen, and oxygen in the starlight suggests that the raw ingredients for chemistry and potentially for life are present. We are learning that our solar system is not a unique recipe, but one of countless variations. The thousands of exoplanets discovered by Kepler and TESS reveal an astonishing diversity, from scorching gas giants orbiting perilously close to their stars to rocky worlds nestled in the temperate habitable zone, where temperatures could allow liquid water to pool on the surface. Each new world, detected by the flicker of its star, expands our understanding of planetary possibility. This intimate connection between the light of a star and the potential for life on orbiting worlds invites a deep reflection. The very atoms that make up our bodies were once part of a star that lived and died long before our sun was born. We are not just observers of the cosmos, we are a part of it, our own story written in the same elemental language as the starlight we study. These cosmic coincidences run deeper than we might first realize. The very fact that we can see ancient starlight at all depends on a delicate balance of the universe's fundamental forces. Consider the transparency of space to visible light. If the force that binds atoms together were slightly weaker, the fog of the early universe might never have cleared. If gravity were significantly stronger, stars would burn through their fuel in a cosmic blink, collapsing into black holes before complex life could ever arise. We exist in a universe with constants that allow for long-lived, stable stars, clear lines of sight across billions of light years, and atoms that interact with light in a predictable, decipherable way. This collection of fortunate circumstances is what scientists refer to as the Anthropic Principle. In its simplest form, It states that the universe we observe must be compatible with the existence of observers. It is a statement that seems self-evident, yet its implications are profound. We are not merely passive witnesses to a random cosmos. We are products of its specific and seemingly fine-tuned conditions. The fact that we can trace the history of helium from the first few minutes of the Big Bang, or measure the iron content of a star 1,000 light-years away, is not a trivial detail. It is a consequence of a universe whose laws are just right for chemistry, for planets, and for the emergence of beings who can look up and ask why. Some theoretical physicists propose that our universe is just one of countless others in a vast multiverse, each with its own random set of physical constants. In this view, we simply find ourselves in one of the rare bubbles where the numbers lined up perfectly for life. Others see the fine-tuning as a clue pointing toward a deeper, more unified theory, where these constants are not arbitrary but are the necessary outcome of a single, elegant law. Whichever perspective resonates, the result is the same. Our ability to decode ancient starlight is a privilege built into the fabric of reality. The light that has traveled for eons is not just a message. It is an invitation to understand our own place in a cosmos that seems strangely fit for discovery. This philosophical grounding transforms our quest from mere day, a collection, into a profound human endeavor, one that connects the deepest laws of physics to our own capacity for wonder. This cosmic curiosity has always been deeply practical. For thousands of years, sailors on the open ocean looked to the stars, not as distant suns, but as a fixed celestial map. They navigated by the consistent positions of constellations, using starlight itself as their guide across trackless waters. That ancient practice of celestial navigation is a direct ancestor of the technology in your pocket today. The Global Positioning System, GPS, is a constellation of satellites orbiting Earth, each one carrying an incredibly precise atomic clock. For the system to triangulate your position, the timing signals from these satellites must be synchronized to within nanoseconds. But these satellites are moving at high speed in Earth's weaker gravity, and according to Einstein's theory of relativity, this causes their clocks to tick at a slightly different rate than clocks on the ground. If we did not correct for this time dilation, an effect predicted by our understanding of light and motion, the GPS would become useless, its accuracy drifting by several miles each day. Our comprehension of how light behaves in a relativistic cosmos is what keeps your digital map perfectly aligned with the real world. The same principles of spectroscopy that we use to analyze a star's composition have sparked revolutions in our daily lives. The laser, a device that produces an intense, focused beam of a single pure color, was first understood through the quantum mechanics of how atoms absorb and emit light. Today, lasers are everywhere. They read the data on your DVDs, perform delicate eye surgery, and form the backbone of the internet, carrying information through fiber optic cables as pulses of light. In medicine, the technology derived from spectroscopic analysis allows for magnetic resonance imaging, or MRI, which peers safely into the human body by manipulating the subtle magnetic properties of atoms, a principle rooted in the same physics that creates the spectral lines in starlight. Even the way we handle information has been transformed by the cosmos. The vast, complex datasets from telescopes like Hubble and Webb, containing the light from millions of galaxies, required the development of sophisticated new algorithms to find patterns and separate signal from noise. These cosmic data processing techniques have become foundational to modern machine learning and big data analytics. The same methods used to identify a distant, faint galaxy in a sea of noise are now used to improve medical diagnostics, forecast weather with greater accuracy, and even recommend your next favorite film. By striving to understand the universe, we were forced to create better tools for understanding our own world. This ongoing cycle of discovery and innovation demonstrates that the quest to decode ancient starlight does more than satisfy our curiosity about the past. It actively builds the technological future, proving that when we look up at the stars, we are also charting a course for progress here on Earth. Each photon from the edge of time is a prize wrested from a sea of interference. Our own atmosphere, a life-giving blanket of air, is a shimmering, turbulent curtain that blurs the light from distant stars, smearing their delicate signals. Even the most powerful ground-based telescopes see the cosmos as if from the bottom of a choppy ocean. To fight this, astronomers use a brilliant technology called adaptive optics. A powerful laser projects an artificial guide star high in the atmosphere, and sensors measure its jitter in real time. A flexible mirror, changing its shape 1,000 times per second, counteracts the distortion, sharpening the view until a distant galaxy snaps into stunning clarity. But some challenges cannot be corrected from the ground. The pervasive glow from city lights creates an orange veil that washes out the faintest cosmic objects, while the growing constellations of communication satellites now scratch bright, frustrating trails across long exposure images, erasing precious data. To escape this, we must go to space, to the silent, dark vantage point above Earth's glow. Yet even there, the data is never perfectly clean. Energetic cosmic rays from across the galaxy constantly pepper the detectors of telescopes like Hubble and Webb, creating false signals that must be meticulously identified and removed by sophisticated software. A digital cleansing to reveal the true, ancient light beneath. To gather enough of these precious photons, astronomers must often stare at a single patch of sky for dozens of hours, sometimes even hundreds. These marathon observations are a test of patience, accumulating light particle by particle to build a signal strong enough to separate from the relentless background noise of the universe itself. This global effort culminates in projects like the Vera C. Rubin Observatory, which will use a colossal camera to photograph the entire visible sky every few nights, generating a vast, living movie of the cosmos. Its success relies on international collaboration and advanced computing to sift an avalanche of data for the subtle changes and faint glows that hold the deepest secrets. Every clear image of a primordial galaxy, every precise measurement of an early quasar's spectrum, is a triumph not just of technology, but of human ingenuity and perseverance. It is a reminder that the universe's oldest stories are written in whispers, and listening requires us to build the quietest rooms and the most sensitive ears imaginable. This relentless push to see further and fainter is already driving the design of the next generation of cosmic observatories, instruments that will read the stories written in starlight with a clarity we can now only dream of. These new observatories are not merely upgrades, they are gateways to eras of the cosmos we have only theorized. The James Webb Space Telescope, with its gold-plated beryllium mirrors and sunshield the size of a tennis court, is our most powerful lens for viewing the universe's infancy. Its unprecedented sensitivity to infrared light allows it to see straight through cosmic dust and perceive the stretched, reddened glow of the very first stars and galaxies as they ignited, ending the cosmic dark ages. Soon, it will be joined by the Nancy Grace Roman Space Telescope, a wide-field surveyor that will not just look deeply at a single point, but map vast swaths of the sky with a field of view 100 times larger than Hubble's. Roman will perform a galactic census on an epic scale, discovering thousands of new exoplanets and mapping the distribution of dark matter with a precision we can barely conceive of today through the subtle warping of starlight. On the ground, the Extremely Large Telescope, or ELT, is rising from a Chilean mountaintop. Its 39-meter primary mirror, a mosaic of almost 800 hexagonal segments, will collect more light than all of the major research telescopes of the past combined. With this colossal eye, we will not only capture direct images of exoplanets, but we will also analyze their atmospheres for the chemical signatures of life, the so-called biosignatures like oxygen and methane. The data from these giants will be a fire hose of information, a torrent of photons from across time. To make sense of it all, we will rely on a new kind of cosmic detective work. Advanced interferometry will combine the light from multiple telescopes, creating a virtual instrument with the resolving power of a telescope as wide as the entire Earth. This will allow us to see the surface features of distant stars and watch matter spiral into the black hole at the center of our own galaxy in real time. Meanwhile, sophisticated computational analytics and artificial intelligence will sift through petabytes of data, finding patterns and correlations invisible to the human eye, synthesizing these separate streams of observation into a single, dynamic, and ever-evolving model of cosmic history. This immense technological leap is more than a scientific endeavor. It is a profound cultural investment. We are building the tools to answer questions that have haunted humanity since we first looked up at a dark sky. Are we alone? How did everything begin? What is our ultimate fate? The light carrying these answers is already on its way, traveling for billions of years. We are simply ensuring that when it finally arrives, we are ready to receive it. This collective effort to extend our vision reaffirms a beautiful truth, that the human drive to understand our origins and our place in the cosmos is one of our most defining and enduring traits. This cosmic perspective, born from Starlight, has forever changed how we see ourselves. The profound realization that the calcium in our bones and the iron in our blood were forged in the heart of a long-dead star is more than a scientific fact. It is a modern creation story. This knowledge echoes through our culture, from the epic scales of science fiction to the canvases of artists trying to capture the sublime grandeur of a universe lit by ancient fires. For millennia, human cultures have woven the stars into their myths and spiritual beliefs, seeing in the constellations the faces of gods and the outlines of sacred animals. Today, we continue that tradition, but the narratives have evolved. They are now informed by the light that carries actual evidence of our cosmic ancestry. Perhaps the most powerful artistic statement of this perspective came from a spacecraft looking back. The famous pale blue dot image, taken by Voyager 1 from beyond the orbit of Neptune, shows our world as a tiny, fragile speck of light suspended in a sunbeam. That single photograph, a direct result of our exploration, delivers a humbling message about the solitude and preciousness of our shared home. Philosophically, this understanding fosters a unique sense of connection. When you look at the faint smudge of the Andromeda Galaxy, you are not just seeing another star system. You are witnessing light that began its journey when the first ancestors of humanity walked the Earth. This ability to peer back through time collapses the immense distances of space, making us participants in a cosmic story that spans billions of years. It encourages a deep humility, reminding us that our planet, our species, and our individual lives are a very recent development in an unimaginably old universe. Yet this is not a call to insignificance, but an invitation to curiosity and stewardship. Recognizing the rarity and fragility of our pale blue dot in the vast cosmic dark can inspire a collective responsibility to protect it. This enriched identity, as temporary custodians of a world built from starlight, empowers us to look forward. The journey does not end with professional astronomers. The tools to connect with this cosmic history are now available to anyone with a sense of wonder. That cosmic story is no longer reserved for a handful of professionals with massive telescopes. Online platforms like Galaxy Zoo and Zooniverse have flung open the doors to discovery, inviting everyone to become a cosmic archivist. Imagine a researcher with 1 million images of galaxies, each one needing a basic classification. Is it a spiral, an elliptical, or a strange, merging pair? This is a task where the human brain's innate pattern recognition excels, And it is a task that has been shared with the world. By logging on, a student, a retiree, or anyone with curiosity can help sort the cosmos, clicking through real data from observatories and often making the first human eye to spot a truly peculiar object. This is citizen science in its purest form, a global collaboration that turns public curiosity into tangible research. The data you help classify goes directly into papers that map the universe's structure and evolution. It is a profound democratization of knowledge, where the light collected by a billion-dollar telescope is interpreted with the help of a global community of volunteers. This spirit of shared discovery extends to the night sky itself. Amateur astronomers in backyards around the world act as the vigilant sentinels of the cosmos. With their own telescopes, they regularly monitor the subtle flickers of variable stars, whose changing brightness provides clues to their internal physics. They are often the first to spot the sudden, brilliant flare of a supernova in a distant galaxy, alerting professional observatories to turn their powerful instruments toward the new event. This partnership between amateur and professional creates a continuous, watchful network, ensuring that the transient fireworks of the universe are rarely missed. The journey of understanding is then shared through the immersive domes of planetariums and the compelling narratives of documentaries. These experiences translate complex data into a sensory spectacle, allowing you to feel as if you are flying through a nebula or witnessing the collision of galaxies. Online courses and public lectures break down the barriers further, offering structured pathways to grasp the principles of redshift and stellar evolution. This collective effort does more than just spread information. It builds a global community bound by a shared sense of wonder. By participating, whether through a click or a telescope eyepiece, you gain more than knowledge. You gain a personal connection to the epic narrative written in light, a visceral understanding that you are part of a species capable of collectively unraveling the mysteries of its own origins. This collaborative spirit, from the professional to the public, ensures that the quest to understand ancient starlight remains a vibrant, living, and deeply human endeavor for generations to come. This entire cosmic story can become your own personal journey of discovery. For anyone feeling inspired to look deeper, a universe of learning is just a click away. Prestigious universities now offer free online courses in astronomy and cosmology, bringing the lecture hall directly to you. Space agencies like NASA provide stunning interactive simulations that let you pilot a virtual telescope through the galaxy, watching how light bends around a black hole or how the first stars ignited. If you prefer to curl up with a book, authors like Neil deGrasse Tyson and the late Carl Sagan have a gift for translating the poetry of the cosmos into language that resonates with wonder, making the physics of starlight feel both intimate and grand. For a more hands-on experience, your local science museum or planetarium likely has an exhibit on light and the universe's expansion, where you can see a spectrograph in action or stand beneath a dome filled with a projection of the ancient cosmic microwave background. The digital world is also rich with resources. YouTube channels and podcasts created by passionate educators and scientists break down the latest discoveries, from new Webb telescope images to the ongoing hunt for dark matter, turning complex papers into engaging stories you can enjoy on your daily commute. And for the truly adventurous, the data is waiting for you. Platforms like the Sloan Digital Sky Survey offer public access to the same vast celestial maps used by professional astronomers. You can download the spectrum of a distant quasar, measure its redshift yourself, and feel the thrill of directly analyzing light that has traveled for billions of years. These tools collectively build a bridge, transforming the awe you feel when looking at the stars into a tangible understanding of the physics and history behind that glow. By engaging with these resources, you are not just a passive observer. You are an active participant in the human quest for knowledge. This foundational learning empowers everyone, from a curious student to a lifelong learner, to appreciate the profound narratives carried by ancient starlight. It prepares the next generation of explorers to tackle the enduring mysteries that still whisper to us from the dark, questions that push the very boundaries of what we know. Yet the cosmos still holds its deepest cards close. For all we have decoded, profound mysteries linger at the very edge of our understanding, questions that the next generation of starlight may finally answer. We still do not know what dark matter truly is, only that its invisible gravity holds galaxies together. We cannot explain why dark energy's repulsive force dominates the cosmos, driving its accelerating expansion. The exact sequence of how the very first stars ignited from pristine gas remains a theoretical puzzle, one we have yet to observe directly. And of course, the ultimate question persists: is life a singular cosmic accident or a common feature of the universe? Each of these enigmas is a frontier, and ancient light is the key that will unlock them. Future observations might capture the faint imprint of primordial gravitational waves, ripples in spacetime from the universe's first explosive moment, offering a glimpse into a realm before the Big Bang we can currently perceive. Some theories even suggest that subtle patterns in the cosmic microwave background could one day reveal evidence of other universes, a multiverse where our cosmic rules are just one local variation. Every new spectrum gathered, every distant galaxy mapped, is an opportunity for a revolutionary discovery that could overturn our current models and rewrite the cosmic narrative from its very first lines. This is the engine of science, the relentless curiosity that ensures the study of ancient light will never grow stagnant. It is a field vibrant with the potential for surprise. As we reflect on this journey, a few essential truths come into sharp focus. We have learned that light is a time traveler, a messenger from the deep past carrying encoded stories of elemental forges and galactic evolution. We have seen how the universe transformed itself from a hot, dense fog into a transparent, structured cosmos filled with galaxies, stars, and planets. And we have uncovered the intimate connection between the cosmos and ourselves, that the atoms which form our bodies were forged in the hearts of long-vanished stars. This is not just a history of the universe, it is our own origin story, written in a language of photons and spectra. To gaze at the stars is to look back at our own cosmic ancestry, to participate in a story of unimaginable scale and profound beauty. The quest to read that story continues, driven by the simple, powerful act of looking up and wondering. The journey of a single photon from a distant galaxy to your eye is a story billions of years in the making. Throughout this exploration, we have followed that ancient starlight, a timeless archive preserving the entire history of cosmic development. We have watched as it carried the blueprint of the Big Bang in the cosmic microwave background, witnessed it being forged in the hearts of the first gigantic stars, and seen it sculpted by the invisible hand of dark matter into the vast cosmic web. We have even decoded its redshifted whisper to discover the universe's accelerating expansion, driven by the mysterious force of dark energy. This entire epic is written in a language of physics, a code we have learned to read through our tools of wonder, from colossal telescopes in the silent vacuum of space to the precise prism of the spectrograph. Our unique ability to look back in time connects us directly to these cosmic events, transforming abstract science into a profound personal discovery. It fosters a deep sense of wonder for the universe and a corresponding responsibility for our fragile, pale blue dot within it. The astronomer Carl Sagan expressed this connection perfectly when he said that we are a way for the cosmos to know itself. In studying the light from these ancient suns, we are not just exploring distant space. We are uncovering our own origin story, written in the elemental ashes of long-dead stars. So the next time you find yourself under a clear, dark sky, take a moment, look up at those points of light, and remember that you are not just seeing stars. You are receiving messages from the deep past, a direct visual link to the universe's formative years. Let that feeling of connection sink in. Then, I would love to hear your thoughts. What does this cosmic perspective mean to you? Share your reflections in the comments below. And if you enjoyed this journey through time and space, subscribe for more adventures into the mysteries of the cosmos.